Good evening, one and all. We are Team CEP from CEPT University, India. Today we will be presenting our work done for the IBIPSA BS2025 Student Modelling Competition. A small brief about the building given for the challenge, the Bundanon Art Museum and the Bridge, New South Wales, Australia. The bridge positioned above the river valley serves as an accommodation while the gallery houses delicate artworks from various patrons. Some of the contextual challenges are that the site is prone to flooding, bushfires, and frequent grid failures. The gallery has to be environmentally controlled for 365 days for the preservation of the artwork. Given the significance of the structure, our team proposed interventions that required minimal alterations to the building geometry and systems while ensuring optimal outcomes. We approached the challenges in an integrated manner. Challenge 1 and the bonus challenge were dealt with keeping in mind the embodied carbon while choosing materials for envelope optimization of the bridge. The climate analysis and literature study helped us understand the site context and existing conditions that drove our passive design strategies. In the HVAC design challenge, the approach was aligned with the performance requirements of the National Building Code of Australia, ensuring that the systems minimize energy while maintaining the essential conditions for an art gallery environment. Using these as a foundation, we found and developed base cases for the art gallery and the bridge, and through a series of interventions, we were able to optimize both the envelope and the HVAC system effectively. We'll start with our preliminary analysis. Using a 9-quadrant analysis chart based on the ASHRAE 55 adaptive comfort model, we found that only 16.6% of bridge hours lie within the comfort zone, while 24% require sensible heating and nearly 13% need dehumidification. Seasonal trends show a strong heating demand during the winter months from April to September, with only minor cooling and humidity control requirements in summer. So to address these discomfort hours, we applied targeted design strategies such as natural ventilation combined with elevated airspeed using fans, along with seasonal shading that helps shift seasonal sensible cooling hours into the comfort zone. Passive solar heating and insulation were introduced to manage sensible heating needs, while hygroscopic materials were considered to tackle dehumidification requirements. The sensitivity analysis shows that the glazing SHGC is the most influential parameter for cooling, followed by the window to wall ratio. For heating, roof U value and external wall construction are the main contributors, while glazing SHGC has an inverse effect by slightly lowering the heating loads. This highlights glazing and insulation as key areas for optimization. Let's dive right into the main numbers. Using only passive design strategies, we shifted 8,498 hours into the comfort band, reducing uncomfortable hours by a remarkable 94%. But we didn't stop there. With targeted interventions adding electric heaters, we brought active heating down to just 27 hours a year with almost no extra energy use. And finally, we ensured air quality by introducing dedicated ventilation with heat recovery. Next, Vishal will walk you through the strategies that made these results possible.
Now, let me walk you through the first and most cost-effective strategy we used, particularly targeting summer months. Building on the comfort improvements I just shared, we developed a smart algorithm to automatically adjust window openings, driven by ASHRAE 55 adaptive comfort model. The logic is simple. Windows only open if the outdoor temperature is below 27 degrees Celsius and if there is a temperature difference between inside and outside of 3 to 15 degrees. When these conditions are met, the algorithm decides what percentage of each window should open. With this approach, we reduce uncomfortable hours by 1400, demonstrating how much of an impact thoughtful natural ventilation strategies can make. For the opaque envelope, we focused on redesigning the wall, roof, and floor assemblies using materials based on their thermal properties and low emission factors. By optimizing the external cladding and insulation with locally sourced materials, we reduced the U value from zero point 0.7 to zero point 0.2, the roof from zero point 0.3 to zero point 0.2, and the floor from zero point 0.5 to zero point 0.3 watt per square meter Kelvin, significantly improving overall thermal performance by increasing the comfort hours by 506, bringing the total comfort hours to 6523. Our next low-cost strategy tackles solar heat gains and glare. Using solar irradiation analysis, we designed a retractable overhang that blocks high-angle sun on the east and west facades during summer, maintaining indoor operative temperature within comfortable range. In winter, the shading fully retracts, allowing sunlight to pass through the glazing and provides passive heating, ensuring year-round thermal comfort and energy savings. While the facade already met NCC daylight prescriptives, we went further, optimizing for comfort with seasonal shading and high-performance glazing. Following LEED standards, we simulated SDA for different glazing and shading strategies. The final design maintains over 95.7% daylight autonomy, reduces annual solar exposure from 14.4 to 7.6% of floor area, and lets occupants keep blinds open more often, providing a comfortable and visually connected indoor environment. Now Shweta will talk about passive strategies that we integrated.
To maintain strong visual connections with the landscape, we retained the window to wall ratio and integrated a trome wall assembly. This system captures solar energy to passively heat the space in winter, raising indoor temperatures by 7 to 8 degrees and stabilizing them around 22 degrees Celsius. As a result, total comfort hours rose to 7,497 as shown in the graph. After adding the trome wall, we faced a challenge of overheating during summers. To resolve this, we replaced the clear glass with electrochromic glass in the trome wall assembly. This smart glass automatically tints when solar radiation exceeds 150 watts per meter square, cutting solar gain by nearly 80% and preventing overheating as depicted in the graph. While the brief focused on maintaining indoor temperatures within the 90% adaptive comfort band, we also addressed relative humidity, a crucial aspect of thermal comfort. We switched the internal wall finish to gypsum, leveraging its hygroscopic properties as shown in the sorption isotherm curve. Using effective moisture penetration depth simulations, this strategy allowed us to passively dehumidify the space, achieving comfort for an additional 298 hours. As a result, total comfort hours rose to 8,498 hours. Now, Akarshna will discuss the challenge 2.
Thank you, Shweta. Moving on to challenge 2, the HVAC design for the art gallery. Being a below grade building, the gallery contains critical spaces like display areas and condition storage where precise temperature and humidity controls are vital. The base case was modeled from the existing gallery's HVAC system, while the design case was refined through energy modeling. Our analysis on the annual thermal gains and losses of the base case showed that the gallery is made up of very different thermal zones, each requiring specific strategies. The display area is driven mostly by internal gains with nearly 80% of its load from people lighting and equipment. In contrast, the condition storage is heating dominant, requiring stable preservation conditions. The office and foyer are cooling dominant zones with around 40 and 35% of their gains coming from solar radiation through glazing. These differences highlight that a zone-wise HVAC approach is essential to maintain comfort and efficiency across the gallery. In the base case, the system was modeled as a ground source heat pump with a variable air volume distribution system. The ground heat exchanger consisted of 27 boreholes, each 150 meters deep. Two heat pumps were provided to handle both cooling and heating with full humidity control and heat recovery. Air distribution was managed through two AHUs, one serving the display area and conditioned area and the other serving the foyer and office, allowing more efficient fan control. For the design case, we revised the system retaining the ground heat exchanger based on load analysis and performance issues observed in the base case. Cooling was supplied by two water-cooled chillers of 6.2 COP connected in series, which helped minimize cycling losses and improved overall efficiency. For the perimeter zones, a VRF system was introduced specifically for heating since the heat pump alone was unable to consistently maintain comfort conditions. By shifting heating to zone level coils, we achieved finer control and reduced energy for reheating. Finally, we also adjusted humidity control set points by allowing a slightly wider band where possible. We trimmed unnecessary reheat and humidification energy.
Altogether, the combination system offered much better flexibility, efficiency, and zone-specific performance compared to the original base case. The thermal load versus consumption plots for the base case and design case shows that in the cooling profile, the base case shows consistently high electricity use across all load bands. In contrast, the design case follows the load much more closely with a sharp improvement at higher loads. In fact, between 60 and 100 kilowatts, cooling electricity consumption drops by more than 70%. On the right, the heating profile shows a similar pattern. The base case once again demonstrates excessive energy use while the design case delivers steadier and more efficient performance across all ranges. Together, these results highlight how the combination system delivers significant energy savings and improved load-wise efficiency while still maintaining the required environmental conditions across the gallery's diverse zones. Coming to the comfort and compliance, the unmet hours based on ASHRAE standard 90.1 in the design case is 0 hours for all the zones. That is, temperatures meet the set point while the RH is within 30 to 70%. But the unmet hours based on the input parameters for both temperature and humidity limits, condition storage has 2.6% unmet hours and foyer has 9% unmet hours. These many hours require dehumidification alone. For office considering only the occupied hours, the unmet hours are within 2% and the display area also has less than 2% unmet hours for 8760 hours of the year. Now coming to the results. The design case demonstrates substantial energy savings across all major system components when compared to the base case. Heating and cooling electricity consumption were both reduced by 68 and 72% respectively, while fan energy dropped by 73%. Pumping energy, though inherently less flexible, still achieved a 20% reduction. Most notably, humidification energy decreased by 93%, reflecting the impact of optimized humidity set points and improved control strategies. Cumulatively, these measures reduce the gallery's annual HVAC energy consumption from 396 megawatt-hours in the base case to 178 megawatt-hours in the design case, representing a 54% overall reduction. Now over to Samiksha for the challenge 3.
Thank you, Akarshna. Now coming to challenge 3, off-grid energy system proposal for the art gallery. For this challenge, we designed a 303 kilowatt solar PV system carefully angled for maximum output and used open solar to optimize its performance. The system generates 483,261 kilowatt each year, almost 3 times what the art gallery actually needs. We specified a battery setup with 420 kilowatt and 315 kilowatt batteries, allowing us to operate off-grid for over 7,800 hours annually, essentially covering the entire year without grid dependency. With a total investment of just over 324,000 AUD, this setup delivers energy at 1.92 AUD per kilowatt hour, achieving both energy resilience and cost effectiveness in the line with the project's goals. Thank you for being patient so far. Finally, we arrive at the bonus challenge. For the bonus challenge, we focused on reducing upfront embodied carbon in the bridge facade. The base case was 36.46 kg of CO2 equivalent per square meter. Through material optimization, replacing insulation, improving cladding, and reducing steel, we achieved a 30.7% reduction, bringing it down to 25.44. While electrochromic glass is still the biggest contributor at 9.58, the final design strikes a balance, delivering thermal comfort and daylight benefits while significantly cutting the carbon cost of construction. In conclusion, these results showcase the impact of our holistic approach, delivering high comfort, daylight, efficiency, and sustainability across all challenges. Together, they highlight the project's achievements in energy performance, autonomy, and reduced carbon footprint. Thank you for your time. We are Team CEPT. Now we are open for questions.